I've done this a number of times, gone through this class a number of times, and it's kind of difficult to just jump right into it and say, okay, here's bridges. Because there's always two sides of the equation in the world of structural engineering. There's the loads and there's the resistance. And let's say I started talking about the loads, and I started talking about the different types of dead loads and live loads and da-da-da-da. When we actually start computing them, we got to say, all right, let's compute all these loads. Oh, wait, now we got to go back and start computing things like moments of inertia and section properties and areas and whatnot. And we end up backtracking, and you take one step forward, then you've got to take 2 steps back and go back and cover all of this stuff that you wish, you look back and go, I wish I had just taken some time and just gone through, some of this pedigree, fundamental information at the beginning. So one of the first things that we're going to do is look at section properties. And by doing this now, what it will do is it'll help us sort of speak the same language down the line when we start talking about the dead loads on bridges, the live loads on bridges, how strong bridges are, computing things like plastic moments and yield moments and depths of webs and compression and all of that stuff. We'll be able to speak the same language because we've gone through some of this fundamental information already. So I want to pass these notes out as well. All right, so I think that's all of them. All right, tell you what, this is what I'm going to do. Start at the back. Let's see, 5. There's that. There's that. And I think that's everything. Okay. Actually, I'll just go this way. I'll be lazy. All right. Now this part I'm going to take a little bit of time and sort of dig deep into this set of notes because we're actually starting to get into the nuts and bolts of what it is we're going to do this semester. So I'm going to take my time with this. All right. So I start off with section properties because these are some fundamental calculations that are going to affect everything that we do from here on out. When we do stress calculations, you all remember from strength of materials, right? Remember that whole sigma equals my over I? Remember that? Well, we need I. We need the moment of inertia. We need those properties. That stuff's going to be pretty important. We need those values to do those stress calculations. If you've ever run any piece of structural analysis software, you have to put in I. You have to put in a modulus of elasticity. You need those properties to run the program. When we start doing resistance checks and capacity checks to see if a given element is safe to resist those loads, we're going to need these properties as well. So these are just so fundamental, we might as well get them out of the way and do it first. Okay? Now, I say section properties. I want to make sure everybody knows what I'm talking about when I say section properties. I'm talking about if I take this, bridge beam or what have you, and I use the secret weapon of structural engineering, which is a samurai sword or a lightsaber if you happen to be a sci-fi fan, and I cut a section right through that bridge, and I'm looking at this beam, looking at the deck. I'm talking about the properties associated with this section. Things like its area, its centroids, its moments of inertia, section moduli, all of that stuff. That's the type of stuff that I'm talking about when I say section properties. Everybody okay with that? Okay. All right. Now, I'm not going to talk about the loads in this discussion very heavily. However, I do need to discuss them a little bit so that you can kind of understand the motivation for what we're going to talk about. All right? So in bridges and in structural engineering in general, you've probably heard the term dead load and live load. I don't like to use dead and live in this course because there's so many different types of dead loads and so many types of live loads. I like to call them permanent and transient. So permanent loads are loads on the structure that are always going to be there. Things like the self-weight of the beam, the concrete slabs, the barriers, if there are lights on the bridge or any utilities on the bridge, the asphalt, if there's asphalt or any bituminous overlay or anything like that. all the permanent loads on the structure. That's a category in and of itself. The other category are the transient loads, the vehicular traffic, dynamic impact, if we're going to consider any seismic effects or anything like that. Stuff that's not always on the bridge, stuff that moves. Okay? What makes bridges unique, and specifically the case when you're dealing with a composite structure, something like this, is that concept of staged construction. So I want you to sort of mentally picture what's going on during a bridge construction, during a typical bridge construction. So let's say I'm trying to cross a bridge from here to here. Okay, so I've done all my earthwork, done all my grade work and what have you, and I've driven piles or whatever, and capped my abutments, and I'm ready to place my girders. So what happens? Excuse me. First thing I do is I take the beams, I set them down, right? Okay, so what loads are the beams subjected to right then? What loads are they subjected to? What's that? They have to support their own self-weight, right? Obviously, all beams have to support their own self-weight. Well, what is resisting that load is the steel beam by itself, just the steel beam, okay? Then I start connecting and everything, putting all the cross frames or diaphragms or what have you in, and erecting the rest of the superstructure. Then it's time to start getting ready to put the deck in. So, setting in all our form work and what have you, starting to tie up our rebar and what have you, getting ready to pour the concrete. Then I pour the concrete. Again, all those loads have to be supported by the steel beam by itself. Make sense? Okay. Now, what happens? Concrete cures. It gets hard, right? Concrete cures. All right. For a composite steel bridge, we tend to locate a fair number of shear connectors on the top flange so that that deck and that girder are locked together. That's what it means for it to be composite, that they're bending and behaving together. When I drive a truck over that bridge, it is not just the steel beam by itself resisting the load of that truck. No, it's the steel beam and the concrete acting together. You see what I mean? So we have different sections that are going to matter. When we're looking at the weight of the wet concrete and the self-weight of the beam, we have to consider just the steel shape by itself. But when we're looking at the vehicular loads, the truck traffic and what have you, we have to look at that composite section, the steel plus the concrete. So we have to look at different sections and look at the different properties associated with those sections. So it's a little bit of a loaded topic worth discussing. All right, make sense? Everybody kind of understand where we're at and where we're going? Okay. All right. Now, before we start just taking a nosedive and starting to calculate this stuff right now, I want to take a little bit of time and go into some terminology, some discussion of different parameters that are going to affect what we're going to talk about, things like effective flange width, material properties, the rebar. We're going to take each of these one at a time, and we're going to break them down. I want to make sure everybody knows what we're talking about and why we're talking about it. Okay? So let's start off with the terminology. Okay? And I'm going to take a little bit of time, make sure we're digesting what's going on this slide. So I prepared this just to kind of illustrate some general quantities and some general terms that I'm going to throw out and use throughout the semester so that we're all speaking the same language and we understand what's going on. Start off, let's talk about the beam, the actual steel beam. So we're looking at an I shape, so I'm saying that this I shape consists of a top flange, a web, and a bottom flange. Now, if you're dealing with a rolled shape, like a rolled I-beam, then your top flange and your bottom flange are going to be the same. But on larger span bands, you're not going to use a rolled I shape from the mill. You're actually going to craft a plate girder with a different size top flange than you have the bottom flange. You're going to be able to tailor those flange sizes to meet your given load demand. So you're going to have different, it's very potential, there's a high potential that you could have a different top flange than you would a bottom flange. So I wanted to introduce that notation and make sure everybody's on the same playing field. So if I've got here top flange B times T, I'm saying it's B wide and it's T thick. So this is the width of the top flange, thickness of the top flange. Okay? Sound good? Now, I'm using this notation very carefully because later on when we actually start opening the AASHTO spec and we start actually looking at the equations that are in the specification, I'm doing my best to ensure that this notation matches what's in the spec so that, you know, if I use a capital D to represent the depth of this web, it's capital D in the spec too. So I'm trying to be consistent with that as well. Now the web, I'm going to say it's D deep, and I'm going to say it's, you know, T wide, or the thickness of the web. And then with the bottom flange, same deal. So far so good? Okay. Now, what's going on with the deck is going to take a little bit of discussion because I've got, you know, this effective flange width, integral wearing surface, total slab thickness, structural slab thickness. We're going to take a little bit of time with that, okay? So bear with me. All right, so I'm going to zoom into that a little bit and make sure that we're attacking this, you know, each of these topics one by one. Before I continue, everybody okay with everything so far? Okay, all right. So let's tackle each of these one at a time. Let's start off with this, the haunch. The haunch is what we define, basically what we're trying to do with the haunch is we're trying to represent the fact that there is, in actuality, a little bit of a gap between the girder and the deck. And you're thinking to yourself, wait, is the deck floating in space? No, it's not. What's going on is if you look at typical forming methods for how we form decks, you look at a lot of these SIP forms, they tend to have, you know, these flutes to sort of receive the wet concrete. And because of that, if we sort of, you know, strike a line, we'll find that the beginning of that flat portion of the bottom of the slab is actually a little bit higher up from the beam. There's actually a little bit of a gap. So in order to be conservative, we tend to neglect all that concrete below the flutes. Okay? Does that make sense? So there is a gap usually. Now, in terms of specifics, so that we're all speaking the same language, what I'm defining as the haunch, I define it as the distance from the top of the web to the bottom of the slab. Okay? So, for instance, if this flange is, I don't know, 3/4 of an inch thick, and this haunch is 2 inches, that would make this little gap, what, 1.25 inches? Everybody with me on that? So I just want to make sure we're all speaking the same language. Okay? Now, does everybody understand what's going on with the forms and why it tends to be raised up a little bit? Okay. One thing to keep in mind is something I've been pretty fast and loose on. We will actually spend a fair amount of time this semester looking at just the studs themselves and actually figuring out how many studs need to go on the beams and in what spacing. The only point I'll make is if you look at a steel beam in a building as opposed to a steel beam in a bridge, there is an ocean of studs on bridge beams, okay? And the reason can be summed up in one simple word: fatigue, okay? Unlike buildings, and don't get me wrong, buildings see these types of forces as well, but in no way, shape, or form at the same magnitude. Bridges see a lot of cyclic loading. They're loaded, unloaded, loaded, unloaded. Trucks drive over and over and over again. And because of that, what can happen is, you know, elements like shear studs and connections and what have you, and those fabrication details, they can experience failure at really, really low stresses. To give you somewhat of an analogy, have you ever taken a paper clip and bent it back and forth a few times and then it kind of just gets softer in your hand and it kind of snaps? You know what I'm talking about? That's what's called low cycle fatigue, because you do it, you know, only a few times and the paper clip fails. What we're doing is we're not applying those very high stresses, but we're doing it millions of times. So we get, what can happen is you can get failure limits that are a lot lower than you would think. You know, steel tends to have a yield stress, or at least a pretty common grade for what we use in bridge applications, of 50 KSI, so 50,000 pounds per square inch. But we can have fatigue categories that can fail at 6 KSI or 8 KSI or what have you. So just worth mentioning. Okay. Just real quick, typical dimensions for the haunch, I sort of went off, but bear with me. This is bridge engineering. I'm going to go off topic quite a bit. Typical values for haunches are anywhere from 2 to 4 inches. A really common value is 2 inches. We're going to use that for an example here in a little bit. All right. So that explains the haunch. I want to talk a little bit now about this concept of an integral wearing surface, because if you notice, I've got 2 slab thicknesses. I've got a total slab thickness and a structural slab thickness. The difference is that the structural slab thickness is a tad thinner, and it's a tad thinner by this integral wearing surface. The reason for including this is over time we tend to assume that a small little layer of that concrete deck is going to go away. Okay? And there's a number of reasons. Just general wear and tear, that's a big reason. You know, the truck scraping the snow and the ice off the bridge, that tends to wear the concrete out over time. So what'll happen is we'll want to make how's the best way I want to put this? We'll want to make a delineation between, you know, how much concrete we're actually considering for capacity and how much concrete was there when it was cast. So to give you an example, we might cast, like when we're out there in the field and we're pouring the bridge deck, we might pour 8.5 inches thick concrete deck. We might pour 8.5 inches. But over time, we're going to assume 1/2 inch of that's going to go away due to it getting scraped off, due to wear and tear, and what have you. The point is, when we calculate loads, you know, the loads that are on that structure, we're going to want to use the total thickness, okay, the full 8.5 inches. But when we're on the other side of the equation calculating the resistance, how strong that given element is, we can't count on that full 8.5 inches because we're assuming some of that's worn away. So we're only going to consider the structural thickness. We're only going to consider the 8 inches. Does that make sense? All right. And each state tends to use different values. One thing I haven't really mentioned this, and we'll talk about this more probably next week when we start digging a little deeper into the specification. But in America, we have a national AASHTO LRFD specification, which is the specification we're going to cover in this course. And the way that works is AASHTO is sort of the minimum standard, okay? But each state can come in and say, well, I have increased standards. And here's a common example, or a simple example to go off of. So AASHTO has a standard vehicular model, a series of loads that they use to represent truck traffic in the United States, typical truck traffic. And that's the model that is the minimum standard across the country. But you go to Kentucky, and Kentucky says, that's great, we're going to use a model that's 25% larger, okay? And that's because in Kentucky they see larger loads, and that's what they need to use. So that specification makes sense for Kentucky. And every state sort of has their own flavor and own preferred construction practices and preferred specs, and it is what it is. It's one of the things that you have to negotiate when you're a bridge engineer. So one state, though, where the regulations are very interesting is Pennsylvania, because they sort of have their own complete way of doing things. There's a common saying among bridge engineers that when you're designing bridges, there's Pennsylvania and then there's 49 other states. So but that's another story for another day. Okay, so far so good? All right, so let me go back to this. So I wanted to talk about the slab thickness, you know, so how we've got this these different definitions between a total slab thickness and a structural slab thickness. I wanted to define what's going on with this haunch. Next thing I want to do is I want to talk about this concept here, this effective flange width. What do I mean by that? Okay, so what I want to do is I want to look at a generic cross-section for a bridge. And I just wanted to use this for the purposes of discussion. So keep it simple. We got 2 12-foot lanes, 2 5-foot shoulders. That's a pretty typical highway bridge in the United States. Yeah, that's pretty typical. All right. So I've got this cross-section here. There's nothing magic about it. This is just set up for the purposes of discussion. Okay. Now, what I want to do when I'm evaluating a given beam, you know, let's say this beam or maybe this beam, is if I'm looking at the composite beam, it's the steel plus a portion of the deck. The key word is a portion. For this beam, let's say if I'm looking at this second beam over, the question I'm trying to answer is how much of that beam is applicable for, or how much of that deck is applicable for this given beam? Is it this much? Is it this much? Is it this much? How much of that deck can I consider effective for that beam? Okay? And if you, I have a 4 there for some reason. That's going to bug me. Oh, enable editing. Sorry, I don't know what happened there. I was playing around with this right before class, so of course I had a typo in it. Now, mechanically, what happens is, if you look at the stresses in the deck, they tend to decrease away from the beam. So what we try and do is we try and cut out a representative slice of that deck and say, okay, that's the portion of the deck that's effective for that beam. If you've had reinforced concrete design, you've done something pretty familiar or pretty similar when you look at T-beams. You've got a floor system that has a slab and a series of rectangular beams, and when you look at that in a composite state, you cut out a slice of that slab and you've got a T-beam, right? I'm sure you all have done something similar when you took concrete design. And when, if you look at the American building spec for effective flange width, there's all these weird little rules, like it's the minimum of the span length over 4, or all these different categories. We kept it pretty simple in the bridge industry. So I have here a small little snippet from the spec, and I'm going to read through some of it, but I'm just going to read this out. So, unless specified otherwise in a series of articles, which we can talk about later, the effective flange width of a concrete deck, slab, in composite or monolithic construction may be taken as the tributary width. Okay? So if you remember from structural engineering, if you've got a series of loads on a given floor system and you want to determine how much load goes to a given beam, you just use the tributary width, which for a given beam is halfway between adjacent girders. That tributary width and that effective flange width are the same thing in the bridge spec. There was a series of studies done, I want to say it was like 2006, 2007, where they were trying to just ask the question, can't we just use this and just keep it simple? And the answer was, yeah, close enough for government work. So the tributary width and the effective flange width are the same thing in terms of the bridge spec. One thing, though, is that can create a little bit of a complication when you're analyzing the bridge, because if I look at the interior beams versus looking at the exterior beams, they've got different effective flange widths. Like, if I look at this one, it's what? Like, what, 10'6"? But this one over here is what? That plus half that. That's not 10'6", right? Make sense? So because of that, I can have different section properties for interior girders and exterior girders. Make sense? So one thing about this course and about bridge engineering in general is make sure you're cognizant of your bookkeeping, okay? Making sure you're well organized with what you do. All right. Sound good? Okay. All right. Now I'm going to bring it back a little bit and go back to strength of materials. I don't know how long it's been since you took strength of materials or mechanics of materials or mechanics of deformable bodies. There's like 8 or 9 different names for the class, but it's all the same thing. This goes back to that whole sigma equals my over I. Everybody's heard that before, right? You know what I'm talking about there, right? Well, sigma equals my over I, if you recall, assumes that you've got a beam made of a single material, that beam is made only of steel, or it's made only of aluminum, or only of copper, or whatever. Well, we got a problem here because we got a beam that's made out of steel and concrete. How do we handle that? Well, we take one of those materials, in this case we take the concrete, and we transform it into an effective lump of steel. Okay? If you've taken reinforced concrete design, you do something similar when you calculate deflections, but it's actually the opposite. You take the rebar in the bottom of the beam and you transform it into an effective lump of concrete. Here what we're doing is taking the concrete and transforming it into an effective lump of steel. So what ends up happening is if you've got this effective flange width, because steel is so much stronger than concrete, this concrete is then represented by this smaller lump of steel. So we transform it by dividing it by N. N is the modular ratio. So I'm sure you all have seen stuff like this before in concrete design, am I right? Okay, all right. So E is the modulus of elasticity of steel, E sub S. E sub C is the modulus of elasticity of concrete. All right. Steel, folks have had me for steel. What is the modulus of elasticity for steel? It's the one number I said you are not going to forget. So there we go, 29,000 KSI. There we go. What did you say? Big money, no whammy, no whammy, no whammy. Stop. Wah, wah. References from the 80s. Gotta love them. All right, all right, real quick. So modulus of elasticity of steel, modulus of elasticity of concrete. When we calculate N, we typically round it to the nearest whole number. Don't worry, if you feel like I'm throwing out like a massive amount of details at you, we're going to practice some of these with a quick example here in a little bit. So don't worry, we'll exercise these pretty quickly. But typically we round N to the nearest whole number. We don't use an N of 7.962. We just say 8. Just keep it simple. Now for steel, the modulus of elasticity of steel is 29,000 KSI. For concrete, we have to compute it, but if you're dealing with normal weight concrete, there's a pretty easy shortcut. We just take 1820 times the square root of FC prime in KSI, and that'll give us a shortcut answer really quickly. All right. So far, so good? Okay. All right. So since we've gone through and talked a little bit about the terminology, let's actually start breaking down the sections that we need to compute. Now, I'm going to take my time with this to make sure that this makes sense, because when we talk about the loads, we will really dig this in significant detail. But I wanted to at least cover a little bit of it so what we say makes sense. When we consider our load sequence, and I'm just going to leave it at this for now and discuss it in more detail later, but when we consider our load sequence, we have to consider 3 types of loads. We consider permanent loads and transient loads, but I'm splitting up the permanent loads a little bit. I'm saying permanent loads that are applied before the section achieves composite action or before that deck cures, and then permanent loads after the deck cures. So what do I mean by after the deck cures? I mean things maybe like concrete jersey barriers or overlays or future wearing surfaces or things like that. There are loads that are applied after the deck is cured, but there's obviously a significant number of loads that are applied before the deck cures. So I'm splitting that up into 3 categories, and also the transient loads. Now, the permanent loads that are applied before the concrete cures, before we get composite action, they have to be resisted by the steel beam by itself. So that's section number 1, the non-composite steel section, just the steel section by itself. Okay? The transient loads have to be resisted by the composite section, the steel and the girder acting, or the steel and the concrete acting together. When I drive a truck on the bridge, the deck and the girder are acting together to resist that load. Okay? Now for terminology, I'm going to call this the short-term composite section, because those loads are only on the bridge for a very short period of time. Truck drives on and it's off, and then it's gone. Okay? Now, to determine the short-term section, I take that effective flange width and I divide it by N, that modular ratio. Sound good? Okay. Now, here's where I want to take a little bit of time. Remember that I was talking about those permanent loads that are applied after the deck cures, things like the barrier, bituminous overlay, future wearing surface, utilities, things like that. They're on the bridge all the time, okay? They're not going anywhere, okay? Now, if you've had pre-stressed concrete, you know as well as I do that concrete is a material that's properties change over time. Concrete undergoes things like creep and shrinkage and what have you. And if you've had pre-stress, you've heard this stuff before. Well, because of that, concrete's properties not only change over time, but they get a little bit weaker, okay? So when we look at these loads, these permanent loads that are applied after the deck is cured, because they're there all the time and they never go away, they're applied on the long-term composite section, okay? In the long-term composite section, we take that effective flange width, we don't divide it by N, we divide it by 3N, so we're dealing with a smaller deck. And we do that because over time, you know, we have creep in the concrete and those effects that can tend to weaken it, okay? So if we're looking at sections in positive bending, we have 3 section properties we have to assess. The steel beam all by itself, the steel beam plus the composite deck, you know, short term and then long term. Make sense? And then keep in mind, these two can be different if you're looking at interior girders versus exterior girders because that dimension can be different. Everybody good? Now, that's positive bending region, where smiley face, where the concrete is in compression. When the concrete is in tension, we have another one we have to consider. We can't always use just the steel plus the concrete because in negative bending, like a region that you would see right here, this region over the pier, the concrete is bending like, or the beam and the bridge is bending like this. So the concrete is in tension. Make sense? So what we've got to do is look at a 4th section which consists of the steel and the rebar. The steel and the reinforcement inside that section. Now, we can do this 2 ways. We can break out the bridge plans, start cutting up the flange width, and literally count every single bar, and then try and do that. No, I'm not doing that. I'm going to come up with a little bit of an easier way of determining that section, and I'm going to do it by looking in the code. Okay? So this is another little snippet from the code. Again, we will take the code in its grand glory later. I'm just identifying given snippets for the purposes of our discussions today. But when you're dealing with negative bending regions, the code specifies that you have to provide at least a minimum amount of reinforcement in those given sections. And instead of counting up every single piece of rebar, what I'm going to do is conservatively assume that I've at least got the minimum. So I'm going to use the minimum. So how's this going to work? I'm going to read the spec, and I've got these highlighted portions for purposes of elaboration. So the total cross-sectional area of the longitudinal reinforcement shall not be less than 1% of the total area of the deck. So that's that one on the left. So what that means is, if I look here at this steel plus longitudinal reinforcement, I would compute the area of this deck and say 1% of that, that's all this rebar. Okay? All this rebar, that's 1% of this area. And how do I lump it? All right? 2/3 in the top layer, 1/3 in the bottom layer. So I take all this area, 1%'s all of it, 2/3 goes up here, 1/3 goes down there. That's pretty vague though. What's this whole up there and down there? Well, I place this rebar according to cover requirements. Y'all remember that? You have to have a certain amount of embedment and for corrosion issues and what have you. I go to the spec and I say, all right, let's look at cover requirements for reinforced concrete. Now for the top, since if we're talking about an area like West Virginia where we're going to have a lot of de-icing salts on the top of the bridge deck, we got to have at least 2.5 inches of cover, okay? So this top layer, that larger top layer, 2.5 inches below the top. That's the cover requirement, okay? And that'll give us our space, all right? For the bottom, up to number 11 bar, we go 1 inch up. So 2.5 inches down, 1 inch up. Sound good? We'll just assume it's all effectively lumped right there. All right, and then for the purposes of our calculation, when we're trying to do spacing, we can just assume that they're number 6 bars, which, let's see if y'all remember. What's the diameter of a number 6? Let's see if we remember. So who said that? They were 3/4, right? Number 6 is 6/8, or 3/4. Whoever said that. All right. Sound good? Okay. So when we're looking at negative bending regions, we have some additional sections to consider. Again, this is just the stuff we want to get out of the way now, so that when we start really talking about the loads, really getting into that stuff, we'll be able to speak the same language.